Hello, today we are going to take a look at how to identify polar equations based on the equation in the graph and be able to match some of those up, identify the different characteristics that are in the equation that are going to and how it will show on the graph. First up, we are going to talk about circles. You know and love circles from geometry and just life in general. And in polar terms, we've got two different types of circles. The first is ones that have the equation r is equal to a cosine of theta. Now, today when I'm talking about cosine and sine, those are going to be interchangeable because the functions will look the same, like it will be a circle, whether it's sine or it's cosine. We'll talk about what the differences are between a sine circle and a cosine circle, but when I say or write one, it will fill in for both for these equations. So let's take a look on Desmos what those look like. We have r is equal to a cosine theta or sine theta. We'll deal with this one in a minute. It is going to be a circle with a radius of this a value. So if we increase a from 1 to 5, our radius has, diameter has increased from 1 to 5. Our cosine function has our x-axis, or sometimes called our polar axis, as a line of symmetry. The sine has the y-axis as our line of symmetry that will bisect it. That is going to be true for all of these polar functions, where cosine will have the x-axis as a bisector and sine will have the y, and that is our major difference, though we'll get into some things with rose curves that are a little different. Now, we also have circles that have the center as the origin, and those are ones where there is no theta, it's just r equals some number. In this case, this is r equals 5. So this has a radius of 5, whereas the other ones had a diameter of 5. Next up, let's talk about this family of polar functions. These, we've got cardioids and then limitones. All of these are going to have the equation in the form of a plus b sine theta or cosine theta. Now, in order to understand what's going on with these and be able to look at an equation and think about what the graph will look like, we need to be able to compare these two numbers, a and b. When we are doing this, it's always going to be in absolute value. So there is a cardioid if the absolute value of a is equal to the absolute value of b. Not sure why I wrote a twice. So here, in this case, a is 1, b is 1. Let's look at the cosine graph. And this is what it looks like. It is a cardioid. The maximum radius here is going to be 2 because we add those two numbers together. Our minimum radius is going to be over on this left side of the graph, as it is going to go back into 0. The sign of a, like SIGN, doesn't matter. If we change this to, let's have this as a step of 1. Same thing with b. That's going to make life easier here. If we change a to -1, it's exactly the same as if a were +1. The sign SIGN of b, the variable that is the coefficient of your sine or your cosine, is the one that matters. When we change b from +1 to -1, the majority of the graph is going to be to the left of the y-axis. And then with sine, If b is negative, most of the graph will be down, whereas if b is positive, the graph will be up. Now, the reason this works out like this is, say we look at that same equation where we've got r equals 1 plus 1 cosine of theta. Look at your values when theta is equal to 0 and pi. So when theta is equal to 0, well, we have r is equal to 1 plus cosine of 0. Cosine of 0 is 1. So our radius is going to be 2. So we have this polar point to 0, which is going to be, well, think of this in the positive direction on the other side. So that is why the maximum radius is those two numbers added together. But then let's look at what happens when theta is equal to pi. Well, we've got r is equal to 1 plus cosine of pi, but cosine of pi is negative 1, so our radius is going to be 0. So we have the point 0 pi. This is why whenever our a and b are equal, both in absolute value, the radius is going to be 0, and that graph is going to pinch back in to the center. So cardioids, our maximum radius is going to be the two numbers added together. The minimum radius is going to be the difference between those two numbers, which is going to be 0 for a cardioid. For the limasones, this is where things are different. This one loop should have kind of like a dent on the one side. It's not going to come back in to have a radius of 0 like with the cardioids. But this is where the absolute value of A is greater than the absolute value of B. And that means the inner loop, the absolute value of A, is less than the absolute value of B. Let's look at some of those and the difference. We'll do the sign here. So let's change it so that A is equal to 2 and B is equal to 1. So A is greater than B. In absolute value, the sign SIGN of B is the one that counts. Let's find where our maximum and minimum radius points are. So up here, we have our maximum radius as 3. We get 3 by adding 1 and 2. Then on this other side, our radius on the smaller side, our kind of dent, is going to be at 1, which is the difference between 2 and 1. Let's change this so that it looks a little bit more like a dent. If A is 3, B is 2. So we've got 3 plus 2 sine theta. Our maximum radius is going to be at 5, 2 plus 3. And our minimum on this side is going to be 1, 3 minus 2. And our equations will work out, and like why that occurs is going to be very similar to why a cardioid has a radius of 0. So if we've got r equals 3 plus 2 sine theta, our maximum radius is going to happen at our sine's maximum value, which is at theta equals pi halves. So r is equal to 3 plus 2 times sine of pi over 2, which is equal to 1. So our radius is 3 plus 2, which is 5. That's how we get our maximum radius. But then our minimum value for sine is going to be negative 1 when theta is equal to 3 pi over 2 or negative pi over 2. That's the nice thing about being in polar coordinates. There's an infinite number of ways to get to the same point. So then our radius is 3 minus 2. So that's why we still have a radius of 1 at that like dent on the other side, or dimple as some people will call it. Now, if B is greater than A, or you want to look at it as A is less than B, we're going to have this inner loop. So let's change A to 1. our rules still apply for what our maximum radius is going to be. Our maximum radius is at 3 because 2 plus 1 is 3. Now, our inner loop happens and has a length of 1 because that's our difference between the two numbers. So let's change this. So maybe A is 3, B is 5. We have our maximum radius. So our outer loop has a length of 8 at its maximum point, 5 plus 3. And then our inner loop has a size of 2 because that's our difference. And again, our sine of A doesn't matter. Our sine of B is the one that matters for direction. When we're comparing the two, we're doing it in absolute value. The positive versus negative does not matter. We end up having a negative radius because if we've got, say, r equals 3 plus 5 sine of theta, our minimum value for sine is going to be negative 1. So r equals 3 plus 5 times negative 1 of like sine of 3 pi over 2. So our radius is going to be negative 2. Since that radius is negative, between some of these values, we're going to end up with that inner loop getting sketched. Next, let's move on to Rose curves, which are going to have the equation of like r equals a times sine or cosine of n theta. And these, we're going to have a petal length of A. So just how long the petals are, P-E-T-A-L-S, not the P-E-D-A-L, because those are in cars. And then our number of petals depends on whether n is odd or even. If n is odd, there are going to be n petals. If n is even, there will be 2n petals. Let's look at what some of those examples look like. So here we have ones. We'll look at the cosine here. Here we've got a cosine graph. The x-axis is our axis of symmetry. It's 1 cosine of 3 theta. So 3 is odd, and we have 3 petals. Okay, nice and easy. We change that petal length from A is 1, 2 to 3 to 4 or 5. And that's just how long each petal is. And then if it's negative, it's just going to cause a reflection over the y-axis or the x-axis if we are talking about a sine graph. This is going to work out in this pattern for any odd value for n. So if n is 7, there are going to be 7 petals. When n is even, however, well, you can also look at like a circle of r equals 3 cosine of 1 theta. You can see it as a circle. You can see it as a petal with length of 1. So it's a flower with a single petal. N is 2. 2 is even. We multiply that by 2 to get 4. And we have 4 petals. The same thing will happen for sine. And that's going to be true when we get up to 4. N's 4, we have 8 petals, and 6, we have 12 petals, and so on. Now, the tricky part here is just identifying which is sine and which is cosine. And here we want to think about substituting values in again. Let's substitute in 0. So theta equals 0. Think about your polar axis just sitting there at its starting point. The sine of 0 is 0. So we're going to have a radius of 0 no matter what your a value is, no matter what your n value is. You're multiplying them both by 0. So there's a radius of 0 here, whereas the cosine of 0 is going to be 1. So the radius of any cosine of these even rose curves is going to be whatever the petal length is. It's going to have that maximum petal. So cosine, the petals are bisected by both the x and y axis. Sine, just going to go between the axes. Let's talk about lemniscates. Those are going to have the equations of r squared, let's do a little darker green, r squared equals a, like, cosine of 2 theta, or sine of 2 theta. It's an infinity sign. A is going to deal with, the square root of a is going to be the petal length. And you can identify these pretty easily based on the fact that it is the only one that's going to be with r squared. The cosine and sine are going to behave just like the even number of petals rose curves, where the cosine will be is pictured here and has the x-axis as an axis of symmetry, and then the sine is going to be between the axes. Last up, let's talk about 2 different types of spirals. We've got the Archimedes spiral, which is frustratingly not the one that's pictured here. And so we'll draw a line, and those are going to have the equation r is equal to a plus b times theta. It looks like a linear function. If we were graphing this in terms of x and y, that's important. We'll come back to it later. Then this is called a logarithmic spiral, which has the function a times b to the theta. Let's take a look at the difference between these two. So this red one is our Archimedes spiral. There is a constant distance between each ring, and that is going to be identified by b. We just multiply b by your theta value, and that's going to cause the change in the size between each ring of the spiral. And it's going to be a constant multiplication there, which looks just like the equation, which is linear, which has a constant rate of change. So that's how you can kind of match those up. And then a is just going to really change. If you look towards the center, that a value is just going to change where that first spiral is going to start. And then b just deals with the size of this. Let's compare that to our, let's get a up here, b up to that. Let's compare that to our blue logarithmic spiral, which is growing at a much faster rate. We should even say an exponential rate, because that's what's happening. If we were to graph all of these out, there would be an exponential difference between the distances of each ring. And that matches up with its equation looking exponential, because that's that distance between them. A is going to change that kind of starting point, just like with our Archimedes spirals, and then B is dealing with that distance in between each ring. So that is the basics of some of these polar equations. Thanks for watching.